Hi everyone and welcome back to my channel A in Economist. So today we will be talking about something called multicollinearity. Multicollinearity is the third violation of assumptions of CLRM. So in CLRM assumption, if you remember, I have stated that for a model to follow classical linear regression model assumptions, multicollinearity should not be present, right? Multicollinearity should not be present. And then if this assumption is violated, if multicollinearity is present in your model, so we have to find out what will be the consequences of that, right? And this is part 18. This is lecture number 18 in our econometrics playlist. If you haven't watched my previous videos, I would recommend you to do so. Otherwise, this will be hard for you to understand, right? So we'll start with the concept. Now, multicollinearity, if you remember, suppose we are using a model like this. Yi is beta 1 plus beta 2 x2i plus beta 3 x3i plus say ui. Suppose this is our model. I know this is a multiple linear regression model which I have not yet covered. I will be doing that once I finish multicollinearity. But the results from multiple linear regression model which I need for my explanation here, I will be stating that, right? Suppose this is the model. Now, what is the concept of multicollinearity? If the explanatory variables that are present in your model are correlated with each other. So, in other words, covariance between x2i and x3i is not equals to 0. If this happens, then we say that yes, multicollinearity is present in your model. So what is multicollinearity? Multicollinearity is simply the correlation or the dependency of the independent variables, independent or explanatory variables that are present in your model. So it's a 3-variable model that I have taken into account, but it could be 4-variable, 5-variable, and any number of variables that you can think of, right? So this multicollinearity concept is associated with MLRM that we haven't yet done, multiple linear regression model. Now, there are two kinds of multicollinearity that might be there in your model. The first type would be perfect multicollinearity, right? The first type could be perfect multicollinearity, and the second type would be less than perfect multicollinearity. Less than perfect multicollinearity. Now, let us talk about each of them in details. Suppose you have k variables in your model. In general, I'm generalizing everything. Suppose you have k variables in your model, namely x1, x2, x3, up to say x3. These are the k variables that are there in your model. And also, you see that there is a linear combination. The linear combination, consider a linear combination for all I from 1 to k. Suppose it is like this. Lambda 1 x1 plus lambda 2 x2 plus lambda k xk which is exactly equals to 0, where the lambda i's are all constant and not all lambda i's are equals to 0, right? So if this is the scenario, suppose you are considering a model which has k independent variable or k explanatory variables, namely x1 to xk, and you find out a linear combination is present. A linear combination is present which looks something like this. Lambda 1 x1, lambda 2 x2 plus lambda k xk, and they are exactly equals to 0. But these lambda i's are certain constants and not all lambda i's are 0. Then what you can say is that there exists an exact linear relationship among the variables, right? If this is the scenario, then you can say there exists an exact linear relationship. Let me write it down. This relation is called exact linear relation. right? Exact linear relation. Now, let the lambda 2 is not equals to 0. Suppose in this relationship, we are talking about this particular relationship here. Suppose this lambda 2 is not equals to 0. Then what you can write is that x2 can be written as minus lambda 1 upon lambda 2 x1 minus lambda 3 upon lambda 2 x3 so on lambda k upon lambda 2 x3. Can you see that? So in this particular relationship, suppose I take all the other variables on the right hand side, only lambda 2 x2 remains, and then you divide lambda 2 with every term. So you will get this particular, right? You will get this particular thing. Now, what can you say from this particular relationship? Can you see anything? From here, what you can say is that x2, the variable x2, is linearly dependent, that to exactly, to the other variables, right? This is, this is very simple to see that here you have x2. So x2 depends on x1, x2 depends on x3, x2 depends on xk. So every x2 is dependent on every other variable that is present in your model. That too exactly, since it is again a linear combination. It's again a linear relationship, right? And in this case, the correlation coefficient between x2 and all the remaining variables is bound to be what? Bound to be what? Can you pause the video and think what will be the correlation coefficient? If you find out the correlation coefficient between x2 and all the other variables, then what will this be if they are linearly related like this? I hope you guessed that right. It will be simply unity. This will be 1. Unity means 1 simply, right? It will be simply 1. And this type of relationship, this type of situation, is called perfect multicollinearity. Perfect multicollinearity. Right? So this is the concept. So as I have told you, multicollinearity can be of two types. Either it can be perfect multicollinearity or it can be less than perfect multicollinearity. So far we have discussed the first case, perfect multicollinearity. So what we have done is that we have considered a multiple linear regression model with k variables, k explanatory variables, and we observe that there is a linear relationship exists. What kind of linear relationship? Exact linear relationship exists. Exact means there is no random term, right? Here this system of equation is exactly, can be determined basically. And also there is no randomness. If there is randomness, that will be the case of less than perfect multicollinearity that we'll be discussing in a while. But see here, all the terms are, can be determined and there is no randomness present in this linear relationship. So exactly the value of x2 can be found out if you consider this particular linear equation, right? So this is the exact linear relationship. And then if you find out the correlation coefficient between x2 and all the other variables, you will see that it will be exactly 1. It will be exactly 1. And this type of situation will be known as the perfect multicollinearity, right? Now, there could be some situations when this multicollinearity is less than perfect, where the x variables where the x variables will be correlated. Let me write though intercorrelated, though they are intercorrelated, but not perfectly. But not perfectly. So they will be intercorrelated, but not perfectly. So what could be the situation? Consider the relationship again. Now suppose the relationship is like this. Lambda k xk and then something, some error term. Suppose you have ui and it is 0 for all, right? Where ui is a stochastic error term. Right? It's a stochastic error term, which basically means it's a random variable. Stochastic means probabilistic. Stochastic error term means UI is a simple random variable which has some distribution, probability distribution. Now, if UI is non-stochastic, then again we would get a exact relationship, right? If this UI would have been, suppose it's a fixed value, it's non-stochastic value, then this relationship and the previous relationship that we have discussed will be no different, because any which ways this will come to the right hand side and the, you know, again the correlation coefficient will be 1. But since it is a random term, now if you find out the correlation, now this correlation will not be 1. It will be something which is less than 1. In this case, in this case, the correlation coefficient, in this case, the correlation coefficient that you will find out will not be unity. Will not be unity, it will be strictly less than 1. It will be strictly less than 1, and this situation is known as, this situation is called less than perfect, less than perfect multicollinearity, right? So I hope that you get the distinction between perfect multicollinearity and less than perfect multicollinearity, depending on the linear relationship among the independent variables. You can find out either perfect or imperfect multicollinearity. Now, one thing you should be noting, that in reality, perfect multicollinearity is very rare. Let me write it down. In reality, perfect multicollinearity exists rarely, right? It's a very rare thing that perfect multicollinearity exists. So what will be this perfect multicollinearity? Let me give you an example. Suppose you are taking into account three variables, x1, x2, and x3. Suppose you have three variables in your model and you see that the variable x1 is taking the value 10, x2 is taking the value 20, and x3 is taking the value 30. If this is the case, then what you can say is that x2 is simply 2x1 and x3 is simply 3x1. So see, x1 and x2 are perfectly correlated with each other. X3 and x1 is again perfectly correlated with each other, which basically means x1, x2, x3. Every variable is correlated with each other. The correlation is exactly 1. Why this is so? This is exact linear relationship. So this is just for an example. I'm just explaining the concept, right? This is just for an example. So this is an example of perfect multicollinearity. But this kind of correlation is very rare in real life, because in real life, randomness has a very crucial role to play in any relationship that you pick up, that you want to model from some real life situation. You will always see that a random term, so for example ui, this randomness will be present whenever you try to model any real life situation. So less than perfect multicollinearity is more common in real life, and this perfect multicollinearity exists rarely, right? So this is one thing that I wanted to share. And now, later on in the next video, I'll be also talking about, if perfect multicollinearity exists, what will be the problem? Why perfect multicollinearity is not assumed? So far, we have only distinguished between what is perfect multicollinearity and what is less than perfect multicollinearity. But our next discussion when we'll see the consequences and all, we will be only talking about less than perfect multicollinearity, right? So since it is more common in nature, less than perfect multicollinearity is what you see in real life. So the next consequences and everything that we will see, that will be based on less than perfect multicollinearity, right? I hope this much is absolutely clear. Now let's talk about the consequences. If multicollinearity is present, what will be the problems? So consequence number one, it says in the presence of multicollinearity, which is less than perfect, as I've told you, that we will be considering less than perfect multicollinearity. Uh, After this, so what will happen? The slope coefficients are best linear unbiased estimator or BLUE, but the OLS estimators have large variances and covariances, making precise estimation difficult. So what this means is that even if multicollinearity is present, the OLS estimators will be BLUE, that is best linear unbiased estimator, which is, a little different from the other violations that we have studied. So under heteroscedasticity, we have said that the estimators are unbiased, consistent, and they're inefficient. The variance was not minimum. Under autocorrelation as well, we have said that they are unbiased, consistent, and inefficient. Again, the minimum variance property was not holding. But the first time under multicollinearity, we see the estimators will be unbiased, they will be consistent, as well as they will be efficient. So these are the basic consequences, right, of the three violations, type of violations that we have studied under multicollinearity. So what we see is that the unique property is BLUE property is still maintained, but what happens is that though BLUE is maintained, the variance and the covariance that you will find out, they will be a very large quantity. They will be not, the exact quantity, they will be large. But that large quantity is minimum, right? They will be large, but that large quantity is minimum that they are they are smaller compared to other measures that you will use for multicollinearity, under multicollinearity. So there will be large variance covariances, but they will still be minimum. So for example, if you consider this particular model, what I am seeing is that suppose this is your multiple regression model. Now, though I haven't done what will be variance of beta 2 cap, I'll be deriving everything in the multiple when I talk about multiple linear regression model. That will be very soon. That video I'll make very soon. So what will be the formula? The formula is something like this: sigma cap square upon summation I small x2I 1 minus R23 square. So this is the formula. So as of now, please just see this formula. I will be deriving everything. So this is the formula. If you want to find out variance of this particular slope coefficient, then this will be the formula. Now, under less than perfect multicollinearity, what will happen? R23 squared will be very high, because since the R23 is the correlation coefficient between the variable x2 and x3. Since x2 and x3 are correlated with each other, they have correlation. So R23 square will be very high, right? Under perfect or less than perfect multicollinearity, these two variables will be correlated with each other. And hence the correlation coefficient between R2 and R3 and the whole square of that will be very close to 1. This will be a very high number, which basically means 1 minus R23 square, this will tend to 0. Which basically means what? This particular thing, if tends to 0, then what will be the variance of beta 2 cap? Variance of beta 2 cap will be tending towards infinity. So if the numerator is going towards 0, then the entire numerator is very low. Entire numerator is very low, and hence the variance of beta cap as a whole, this ratio will be very high. So variance of beta cap will be going towards infinity, keeping sigma cap square constant, keeping this to be a constant value. Where sigma cap square, if you remember, sigma cap square is simply RSS by n minus k. Here k is 3, so it will be RSS by n minus. So we have derived this particular thing also before, if you remember, right? So sigma cap square is simply this. So what we can say is that BLUE property is holding. BLUE property is holding, but variance of beta 2 cap, is tending towards infinity. So minimum variance is tending towards infinity, basically, right? Minimum variance is tending towards infinity. And similar thing can be done using this particular coefficient as well. Variance of beta 3 cap, here it will come as beta, sorry, x3i, right? Everything else will be same. Here only you will have x3i. So I hope you understand the first consequence. So what we have said is that if you consider this linear regression model of multiple variables, here you have two explanatory variable and one dependent variable. So altogether you have three variables, and you find out variance. And again, if you find out covariance as well, you will see this kind of a relationship will appear, where you can say, where you can prove that the variance and the autocovariances will be tending towards infinity, though they are minimum, or though they are lesser than any other estimates, right? So this is the first consequence. Now coming to the second consequence, it says the confidence interval in the presence of multicollinearity tend to be much wider, leading to the acceptance of the zero null hypothesis more readily. So if you remember, what will be the confidence interval? Again, confidence intervals of say beta 2. I find out confidence interval beta 2. So it will be simply like this: beta 2 cap minus t alpha by 2 n minus 3, and then you have standard error of beta 2 cap. So this is the lower bound, and what will be the upper bound? Beta 2 cap plus t alpha by 2 n minus 3, and then standard error of beta 2 cap. So this is the confidence interval. Now, as I have told you, the variance of beta 2 cap is tending towards infinity, right? Variance of beta 2 cap from the previous consequence, variance of beta 2 cap is tending towards infinity. Now, standard error of beta 2 cap is simply the square root of variance of beta 2 cap, right? So it will also tend towards infinity. I hope this much is clear. Since variance of beta 2 cap is tending towards infinity, if you take the square root, it will also be tending towards infinity. Also, there is a concept of variance inflation factor, but since I have not introduced that concept, I don't want to go into that. So I want to explain in this way also only, right? So variance is going towards infinity, and standard error, which is simply the square root of variance, that is also tending towards infinity. Now see, here you have standard error, here you have standard error. So if multicollinearity is present, then this quantity will be very large, and this quantity will again be very large, right? If these quantities are very large, then the confidence interval itself will be very large. See, they are in a multiplicative form. They're in a multiplicative form. If you multiply something with a very large number, then obviously the value will be inflated. So the lower bound will also be inflated, the higher bound or upper bound will also be inflated. So the case is like this. Previously, suppose this is the confidence interval. This is the old confidence interval. But as you introduce multicollinearity in your model, the lower bound also increases, the upper bound also increases. So the new interval itself increases. This is the new interval. So the confidence interval gets inflated. The lower bound and the upper bound of the confidence interval get inflated, and which makes it easier for the acceptance of the zero null hypothesis. So suppose this is the old confidence interval. It's a much smaller confidence interval, so the possibility of accepting zero null hypothesis is lesser. But now, since this is a larger or more wider confidence interval, the possibility of accepting zero null hypothesis will readily increase, right? So zero, so what I'm saying is that the possibility of zero lying in this particular interval is smaller than the possibility of zero value lying in this particular interval, right? This is a much wider interval. So the probability of having zero in a much wider interval is more than the probability of having zero in the smaller interval, right? So that is why I've written that, leading to acceptance of zero null hypothesis more readily. I hope this thing is absolutely clear to you. Okay. Now let's go to the next consequence. Third consequence is, because of consequence 1, the t ratio of one or more coefficients tends to be statistically insignificant, right? So let's see this. What is t? T beta 2 cap, if you find out t statistic, it will be simply beta 2 cap under standard error of beta 2 cap. Now again the same concept, since standard error of beta 2 cap is tending towards infinity, the entire t statistic is tending towards 0. Right? I hope this is clear. since the denominator is going towards infinity, the entire ratio is going towards zero, which means that the possibility, which basically means the possibility of the variable being statistically insignificant is higher. So see, ideally what should have happened? Suppose your H naught is beta 2 equals to 0, that is the variable associated with beta 2, that is H2 is statistically insignificant, versus H1 is beta 2 not equals to 0. Suppose this is the case. Now, what is the ideal scenario? We would have rejected H naught at the level alpha, at the level of significance alpha, if the mod value of t is greater than t alpha by 2n minus 3, right? This is the ideal case. But since under multicollinearity, this t computed value is very small, right? Under multicollinearity, this is under multicollinearity. Under multicollinearity, since t beta 2 cap is going towards 0, it's very small. Then what happened? There is more chance that the computed value of t will be less than t alpha by 2 n minus 3. I hope this is absolutely clear. Now, if this scenario is more likely, then it is more likely that we would not be rejecting H naught, right? If this is more likely, then we will be in the acceptance region and will not be rejecting H naught, which basically means that the variables will be insignificant in nature. The t statistic will be very less, which means that the chance, or the probability of accepting the H naught is very high. I hope this consequence is clear. If you have any doubts anywhere, you can let me know in the comment section and I'll be replying to that, right? So again, let me summarize everything. Under multicollinearity, we have seen that the d statistic will be closer to 0. Now, since it is very small, it is very likely that the computed t value will be less than the critical t value, right? This relationship is more likely. If this relationship is more likely, then it is more likely that we would not be rejecting H naught, because when we would have rejected H naught if the computed value is greater than this. If the computed value falls into the rejection region, then only we would have rejected H naught. But under multicollinearity, it is very likely that we would be in the acceptance region, and hence we would be failed to reject the null hypothesis. And thus, what will be our conclusion? Conclusion will be beta 2 exactly equals to 0, which means that X2 is statistically insignificant variable, right? So I hope this consequence is clear. So what this example is saying, suppose I give you an example. Let me make some space for myself. So suppose I consider a model like this. Suppose I say salary is beta 1 plus beta 2 on the level of education plus beta 3, suppose IQ, plus some random variable, right? So this is the model. If this is the model, then what we know is that salary is dependent on education and IQ. Now you want to test that if education is statistically significant or not, and IQ is statistically significant or not. Now, if multicollinearity is present, it is very likely that this beta 2 will come out to be 0. Which basically means that education is not statistically significant to find out the salary level. But is this true in reality? It is not true in reality. Education is one of the most important determinants of salary, right? This is what we know. So this is the problem. See, what I am saying is that if the variable becomes statistically insignificant, though intuitively we know that they are significant, education is a significant variable intuitively, but if multicollinearity is present in your model, the model will show that no, it is not statistically significant. So herein lies the problem. I hope now this portion is absolutely clear. Now let's move on to the fourth consequence, which says, although t ratio of one or more coefficient is statistically insignificant, the R square, which is the measure of goodness of it, can be very high. So this is also one of the severe consequences. So for detecting multicollinearity, we see two things. Either R square is very high or few significant t ratios. Few significant T ratio. So these are the two things which give you an idea that multicollinearity is present in your model or not. Now see, what happens is that suppose we can take the previous example only, we say that education is not a significant variable. Suppose in your model you see, after running the regression, you see that education is not significant. Education is not a significant variable. So basically, which means that education has no explanatory power. Education has no explanatory power. Education cannot explain the variation of salary. But still, what you see is that in your model, the R square is very high. Right? In this particular scenario, ideally, what should have happened? R square should be very low. If you are saying that your variable, your explanatory variable, is not at all significant, then ideally, what should have happened? R square should have been very low because the model has no explanatory power, which basically means your model has no explanatory power. R square measures the goodness of it. Hence, ideally, in the normal scenario, what should have happened? R square should have been very low. But if multicollinearity is present, you will see that R square is still showing up to be very high. This is the consequence, right? Under multicollinearity, R square will be very high. So what I'm saying is that suppose H naught is beta 2 equals to 0 versus H1 is something, suppose beta 2 not equals to 0. Suppose this is the hypothesis. So under multicollinearity, what will happen? The T statistic will be insignificant, very small. It will be very close to 0. This will be very small. But still what you see, so basically beta 2 equals to 0. This hypothesis, null hypothesis is accepted, which basically means x2 variable that is associated with this is insignificant statistically. But still what you will see, the R square of this model will be very high. R square will be very close to 1 basically, right? So the chosen variable is not explaining most of the variation and still the R square is very high. So this will be one of the severe consequences of multicollinearity. And the final consequence will be the OLS estimators and their standard errors can be very sensitive to the small changes in the data. So if you increase the X value by a very small amount, then also the standard errors and the OLS estimators will be, very sensitive. It means they will fluctuate a lot. Right. So it says the OLS estimators and the standard errors can be very sensitive. Sensitive means they will fluctuate a lot. If you change the X value by a little bit, a small amount of X is changed, then also the value of the estimators and the standard errors will be either they will increase a lot or they will decrease a lot. Under multicollinearity, usually they will increase, right? So because we have already said that standard error is going towards infinity, since variance is going towards infinity. So these are some of the consequences under multicollinearity. I hope you find this video helpful. If you have any doubts anywhere, you can let me know. And in the next video, we'll be tackling two more questions. First question is that if multicollinearity is present in your model, what will be the consequence, right? Why perfect multicollinearity is not seen in real life? And if it is seen, what will be the consequences? We will discuss that question, and also we'll be going into the method of detection of multicollinearity, where that variance inflation factor that I was talking about will come into the picture, right? So thank you so much for your time. And if you find this video helpful and if you want to see more of these videos, then give me a like and do subscribe to this channel AN Economist. This will give me immense motivation to continue making such useful videos for you. Thank you for your time and let's meet you in the next video.